Welcome, AP students. We're going to start the review for your AP test next week. And so I'm going to be putting together some videos and some material that was put together by Miss Aiken last year, which is fantastic. But I'm going to go through and do each big idea as an individual presentation. The first one that we do will be big idea 1, which is atomic structure and properties. And we'll go through and fill out a little cheat sheet that you should have in front of you. If you don't, you can print it off online and then go through or watch me go through the video and fill yours out as we go. This was the first year we did it last year, 2021, and it was, in my opinion, fantastic. It's sort of big picture looking at everything. If there's any individual things that you need, go back and look at your note packets. Go back and look at your Fast Track 205, which is good. And let's go ahead and get started. So I'm going to try to zoom in a little bit and let you kind of see these as we get through here. So this is what it looks like here. This is what your paper looks like. Sorry, you guys don't have color, but whatever. And what I'll do is I'll take you through the entire sheet as a single video, and then we'll come back and do the other ones individually. So the first one is this big idea 1, atomic structure and properties. So starting up here at the top, kind of a definition of matter here. Matter, anything that has mass takes up space. You guys understand that matter is pretty much everything. It makes up everything. If we scroll, I'm going to go this way, going to the left here. So if we go over here, and I'll zoom in a little bit so we can look at these. But atoms are the simplest form of any element. That really is just a definition. One of the ways that we calculate like average atomic mass and the mass that's actually labeled on the periodic table is by multiplying by their percent abundance, and we'll do that in a second. But right here it says, the atomic mass on the periodic table is an average of that mass of all of its isotopes. So maybe you remember what an isotope is. An isotope is basically, it's made up of atoms with the same number of protons, and I'm going to write protons as a P+, but same number of protons, but a different number of neutrons. So different number of, and I'll write in 0 for neutrons. So you'll have things that have different masses, like carbon 12 and carbon 14. Carbon 14 with 2 more neutrons than carbon 12, yet they both have 6, I believe it is. Yeah, I can double check. 6 protons in the nucleus of a carbon atom. But if I'm going to scroll down here, so I've gone down this way here, I'm going to continue to go down here. You're given a graph of percent abundance. And so what you're asked to do in that box right below it, so where I am right here, is calculate the average atomic mass of this particular element. We're given mass numbers in AMUs of 90, 92, and 94. So what I'm going to do is I'm just going to kind of scroll across here and figure out what they are. Scrolling across here, and we're going to assume that these are, pretty much the same. What I would do is I would multiply their percents times their masses. So I have 50%, which is 0.50, and I'm going to multiply that times the 90, and then I'm going to add to it the other masses. I've got one that's 91. I'm going to do 91 instead of the percent first. 91 times, and I'm approximating that mass or that percentage to be about, let's say that's 10%. So 0.10. And I'm going to add to that 92 times, let's use a dot to do the times 0.20. And then I'm adding to that 94 times the 0.20 as well. I'm saying that those two right here both have the same percent abundance. So what do you got? 20, 20, 50, and 50. That sounds about right. If I go and do these individually, this would be 45 for the first set of parentheses there, that first isotope, and then 9.1, and then 18.4, and then adding at the end 18.8. This gives me approximately 91.3 AMUs. Now, when you're doing AMUs like this, as far as significant figures are concerned, really the atomic mass is an exact number. It's the number of protons and the number of neutrons. So really, we would be looking at our percentage for our significant figures there. But anyway, So here's our answer when we add them all up to the right of the decimal place. Debatably, it could be 91, but let's go with 91.3. So atoms found on the periodic table are going to be in families or periods, you know? So I'm scrolling from this box down to this box right here. In periodic table and families and periods according to their atomic number. When things are set up according to this periodicity, they tend to, we tend to see that periodic repeating of properties. And so if I look here, these are periods. So periods, like you remember, I hope, go across the periodic table, 1, 2, 3, 4, 5, 6, 7, 8. And then groups or families go down the periodic table. So families, or they're also called groups. Yeah, you could call periods energy levels. They're really not. Their periods are first, second, third, fourth period. In the fourth period, there can be things in the third energy level, like the D step down in energy level. And so it's better just to call them periods than call them energy levels. But yeah, you get the idea. And so that's where those are found. Let's see, which way do I want to go now? If I scroll over here, we can go this way, talking about the atom still over here. Yeah. So here it says, you know, the atom is composed of a nucleus. Inside that nucleus are protons and neutrons. Those are going to be my abbreviations for protons and neutrons. And then electrons will be abbreviated by, you know, sort of an E minus. But energy, the electrons are actually, and I'll put electrons here so we don't have to say this again through the review, are surrounded by electrons found in energy levels or shells, or if you like, clouds or locations where they are, energy levels or shells, and orbitals. Or we could also call those subshells. You may see that nomenclature. And your subshells and your orbitals are going to be like S and P and D and F. Yeah. Yeah. Coulomb's law determines that attractive force, the attraction for those electrons for that nucleus, that is going to be called, generally speaking, the Coulombic, let's make sure I'm spelling it right, Coulombic force, or the Coulombic attraction. So if you ever talk about the strength of the attraction for the electrons for the nucleus, use Coulombic force to describe that. The formula over here is the Coulombic force of attraction is going to be K, which is a constant, times Q1, Q2 over the distance between them squared. And you can write R squared or D squared. In chemistry, we generally say R squared, the radial distance between those two. You know, as this Q1, that's a Q, and Q2 increases, that ratio of those, that Coulombic force is going to increase. And as the radius increases, the actual force is going to go down, right? So I've got two different things that are happening here. So if I'm adding to this denominator, making it larger, the Coulombic force is going to be smaller. If in fact the charges are getting larger, then it's going to be a larger force as well. But if I think I said that right. If the radius increases, it's going to decrease the force. If the charges increase, it's going to increase the force. If things are very close together and that radial distance is getting smaller, then of course, if you're comparing two things, then that would be a stronger force. So that Coulombic force leads to some periodic trends. And I'll kind of go through these and show you there on the periodic table for these individual trends. But here, ionization energy, this is the energy required to remove a gaseous atom. Or sorry, remove an electron from a gaseous atom. Ooh, tiny. The atomic radius is going to be the distance from the outermost energy level electrons to the nucleus. So this is going to be, let's make this bigger, the distance from the outermost, or the valence electrons. Energy level electrons to the nucleus. And electron affinity is going to be an atom's force on another electron. So what electron affinity is that strength of attraction for those electrons. And this will be dictated by Coulomb's law. All these are actually. And electronegativity is an atom's force on a shared pair of electrons. So it's that Coulombic force of attraction on the electrons in a covalent bond, a shared pair of electrons. Now, if that shared pair, if that number is greater than 2.0, or the difference is greater than 2.0, we're going to consider it an ionic compound, but we'll talk more about that later. So let's scroll over this way. So what we have over here is photoelectron spectroscopy. Now, this is something, still talking about the atom and the nucleus, but a photoelectron spectroscopy kind of tells you where the electrons are. So with a certain amount of how much energy it takes to remove that electron is the ionization energy. What this is showing you the ionization energy of multiple electrons in an atom. So if you're trying to figure out, say, which element this is, or what the ionization energy is of its outermost electron, you could use this data to figure it out. The one that has the highest number are the ones that are closest to the nucleus. So I'm circling it over here. The one that has the highest value, in this case, I think it's millijoules per mole. Is that right? Millijoules per mole is going to be the one that's pulling on them the greatest. So the ones that are there are going to be the ones closest to the nucleus. So that would definitely not be the 2s. That would be the 1s2. If we look at the next one, that is also a peak of 2. Notice the number of electrons is over here on the y-axis, and the strength of that attraction, or the amount of energy necessary to remove them, is on the bottom. So this would be 2s2. Then I've got here 2p6, and then here 3s2. I know it's written right there as a title, but had we not known what this element was and we were identifying by electron spectroscopy, we would call this magnesium. So yeah, the position of the electrons is determined using that PES, or photoelectron spectroscopy. So if you look at this little diagram here, I know it's actually kind of nice. Yours is not in color, but that's all right. In here is going to be your nucleus. That's where your protons and your neutrons are going to be located. And then out here in the outside shells are going to be where your electrons are. And these are spherical, so I would say they are s orbitals, definitely. Had we added some p-shaped orbitals to it, they would have looked kind of like this, probably in the same energy level. I'm doing a little kind of a bad job drawing them, but they would have looked something like that. The position of the electrons can be easily shown using electron configuration, which it's been a while since we've done this, but I know you guys like it, 1s2, 2s2, 2p6, 3s2. If we used magnesium as our example from our PES, we would have written 1s2, and it's written up top like it's squared. We don't say 1s squared, but 1s2, 2s2, 2p6, and then 3s2 would close out the valence electrons for that one. So let's scroll back up to the top and look at what else we have here. So matter, one part of matter is the atom itself. If multiple atoms are together, they're going to be compounds, right? And so that would be bonded groups of atoms being compounds. Let's make this a little bigger there like that. And so ionic is going to be a metal and multiple, depending if it's polyatomic ion, a metal, and I'm going to abbreviate non-metal as NM, non-metal. And they're held by, they're held together by an electrostatic attraction. Yeah. Electrostatic attraction, you could say by that Coulombic force, if you like. That would be fine too. The abbreviation for these is formula unit. If you remember, if you're just talking about a single unit of it, you would call it a formula unit. You can abbreviate that FU. Be careful who you say that to. Over on the right, we've got covalent moleculars. These are where you're going to have 2 or more nonmetals, and they share electrons. They share one pair or more of electrons. So these are going to be These could be, let's just go ahead and say they could be polar, they could be non-polar. They are going to be called molecules. There's not really an abbreviation for molecule. I usually write molec with a, and then put a dot, but that's up to you. Moles, it's a chemical measure. The mole is actually, if you have enough of these, it's a chemical measure of quantity. Quantity actually doesn't matter how many of them you have. You can have some version of how many moles you have. 1 mole, I'm sure you guys remember, is 6.022, if you like, times 10 to the 23rd. I'm going to write particles here, but it could be molecules, formula units, whatever. Remember that we also have molar mass. Just kind of as a reminder, that is the number of grams per mole that you have. So that's compounds, and a little bit extra kind of stuff thrown in there in this unit. Another way of thinking about matter is a mixture of substances put together. So in this case, it'd be a mixture or combination of elements and compounds. Something that is homogeneous is a mixture that is consistent, yeah, or has consistent mixture, I should say, that has consistent, I think that's right. Oh, I thought I left out an F, an S, consistent composition. And so an example would be like NaCl, right? If I put NaCl in water, I would have a homogeneous mixture. It would be consistent all the way through. I wouldn't see parts in it, or it couldn't be separated. Heterogeneous is kind of the opposite, or it is the opposite. It's a mixture that's inconsistent in composition. And so solutions with a precipitate, oil and water, those are heterogeneous mixtures. Salad with a bunch of things tossed in it, that would be a heterogeneous mixture. But for an example here, I'll just go ahead and say, how about a solution with a precipitate? Yeah, or something that has more than one phase. So there's another example, 2 phases. It could even have more than 2 phases, but if it had, say, the oil and water, you would have 2 phases of a liquid. So there are some ways to separate mixtures. One of them is filtration. You're separating the solid precipitate from the solution. So this would be used to separate, and I have, whatever. Separate a precipitate from solution. That's good enough. One of the ways we do this is by gravimetric analysis. Could also use vacuum filtration, would be fine. Distillation used to separate mixtures of liquids by their boiling point. So this would be separate by boiling point. And that would be, of course, liquids. Chromatography is going to separate based on the nature of that substance. So this is separation by the nature of that substance. So like polar or non-polar, how well they mix with the solvent, or how much the solute mixes with the solvent. So there's an example of each. So over here is kind of your separation by gravimetric analysis. You've got a filter and a funnel, and you pour it through, and the solid shows up in the top, right? And then down here would be your filtrate. Yeah, filtrate. Oh, it's written there. Ha ha ha. Will be your filtrate at the bottom. The chromatography is over here on the right. So if you had something that was polar, so if you had, say, polar water, which is just water because water is polar, it would be drawn up the filter paper, right? And so polar water, let's say, how am I going to say this? It goes up, or runs up, I guess you could say. Let's say runs instead of goes, runs up the filter paper. We did this the very beginning of the year in our first lab where we had several different pens and the pens were dragged out based on their polarity, but it would go up the filter paper and pull the polar compounds with it. And it would separate them. The non-polar ones wouldn't travel as far or wouldn't actually travel in the paper. And so the polar ones would. So if we look at this, this would be separated, the polar ones moving. Now, the ones that up here are going to be the ones that are smaller in size. And these would be larger in size. And it may also be a degree of polarity as well. But you can separate them by their components that are inside the actual mixture. So that takes us through the first little lesson, pretty much, I'm sure. Did we do all of it? I think we got through all of it. I don't think I missed anything. If you have any questions, you're welcome to message your instructor and see if there's anything that you didn't understand you want to go back through. I encourage you to look through the Fast Track 205 as an excellent resource. It goes topic by topic through each chapter, and it's an excellent summary of what's in your Zumdahl textbook. All right, guys. So I'll see you in the next review. What is Big Idea? Big Idea 2 will be molecular and ionic compounds, and we'll talk about their structure and some of their properties. Okay.